Okay, good afternoon, good morning, whenever you are watching this video. So we are going to talk about middle boxes in this short video. For the last lecture, I have divided the lecture into a couple of videos. This one is going to be a short one about middle boxes. We are not going to talk about the middle boxes in too much detail. I'll just have one, slightly detailed example, but not too much. Only a couple of dozen slides, and we will be done hopefully in about 25 minutes. Okay, so what are middle boxes? First of all, the agenda is to talk about middle boxes by appreciating the difference between the end systems and network infrastructure. So throughout the course, we have been talking about the network infrastructure as sort of a dumb pipe which is used for transporting packets from one end host to another end host. So the implicit assumption is that the network infrastructure is used for simply delivering the packets to and from the end systems. And most of the intelligence we thought that lies at the end system hosts, such as reliability. Remember when we talked about TCP, TCP was only operating at the endpoints. There was no notion of TCP, no state of TCP within the network infrastructure. Congestion control similarly was taken care of at the endpoints only. You would adjust the rate of TCP sender only by looking at the endpoints. No support from the network infrastructure. So, we have grown up in this course thinking that maybe the network infrastructure is very simple and most of the complexity lies in the end system host. That is not actually true, because in reality, the network infrastructure is also highly complex. There is a lot of intelligent tasks which happen in the middle as well, in the network infrastructure, in between the host. And we have some examples of those. Okay. So I will just give you a few examples in the network infrastructure. Where is the intelligence? So for example, if you want to block the traffic from unwanted senders who are known to be dangerous to the network infrastructure, you might use a firewall for that. The firewall will block the traffic, the packet coming in from those senders which we blacklist, or which we mark as unwanted. Okay. Similarly, what if we want to make the web load faster? We have already discussed web caching for this. If we want to make the web load faster, what I could do is that I could install a cache closer to the client, away from the server, somewhere in the middle in the network infrastructure. So I can include a web proxy cache somewhere within the network infrastructure, whether it is closer to the server, closer to the clients, or somewhere in the middle. We have had a lot of discussion on that in the earlier lectures, but we do know that there is a web proxy or cache which exists somewhere in the network, which is an intelligent component. It's not just a dumb router whose job is just to forward the packets from one port to another port, one interface to another interface. Okay. Similarly, if we want to reduce the number of public IP addresses used, we have also used a device, referred to a device that we call a NAT, network address translation. We gave an example of campus network where we have about 5,000, 6,000 different hosts, 5,000, 6,000 different IP addresses. And these IP addresses are represented by one single IP address leaving the campus network. And that is a network address translation box. All the traffic from the campus, all the host traffic from within the campus is concentrated. And this traffic passes through this NAT box, which translates all the IP addresses, all these different 5,000, 6,000 different IP addresses into one single IP address. Okay. And somehow it knows that when the response comes back, it would direct the response back to the right sender. So let's take a look at how NATs are working. What is a NAT? So this is one of the examples of the middle boxes that we will jump into in slightly more detail. I just have a few slides about this. So NAT is a solution for depleted IP space. What do we mean by that? Let's consider a few facts here. Fact one is that each end host on the internet requires an IP address. We all know that. If I want to communicate, I will need an IP address. Any device which needs to communicate will need an IP address. Okay. The second fact is that these IP addresses cannot be duplicated. Two different hosts on the internet, they must have two different IP addresses. No two devices can have the same IP address on the internet. And the third fact is that there are only 4 billion IP version 4 addresses, IPv4 addresses as we call them out there. 32-bit long addresses and 32-bit, they give you only 4 billion different combinations. And some of that IP address space might even get wasted. Why is that? That is because you allocate these IP addresses in blocks, and it is possible that I will not need a block which is a power of 2. So if I need 15 different IP addresses, I will get a block of 16 different IP addresses. If I need 17 IP addresses, I will not get a block of 17 IP addresses. I will get a block of 32 IP addresses. So those 15 IP addresses will get wasted. Okay. So that is also a fact. The last fact is that fast growing number of hosts, they have already exceeded 4 billion. Very tiny devices on the internet, lots and lots of users using IP addresses for their own devices. So we see that there is already more than 4 billion IP addresses needed on the earth to address all these devices which exceed 4 billion. Okay. So how do we address this situation? We did not have more than 4 billion IP addresses. Maybe instead of using version 4 IP addresses, we use some other kind of IP addresses which are maybe not 32-bit long but longer. Okay, and that is one of the solutions. So some of the existing solutions, actually two of the existing solutions, in the first one is that use IPv6 addresses, IP version 6 addresses, which are 126-bit long compared to the only 32-bit long IPv4 addresses. So there is lots and lots and lots of IPv6 addresses. We are never going to be finished with IPv6 addresses anytime soon. So while IPv6 is deployed on the internet reasonably well, but the penetration is still very, very small as compared to IPv4 addresses. Many service providers have not upgraded their networks to IPv6 addresses. Okay, so this solution, while it works, this solution is not prevalent. The other solution, which is criticized upon, but it works very well and has been deployed quite often, is called network address translation. So in that case, we use a network address translation device to represent a group of internal or local IP addresses, a group of internal or local IP addresses. Okay, so what is network address translation? How do you implement that? So this figure shows an internal network, maybe something similar to a campus network or a company network, or maybe your home network, where all the IP addresses are in the numerical vicinity of each other. So in this particular example, we have this internal network. All the IP addresses here, they start with 10.0.0. The first three octets in the IP address are 10.0.0, and the last octet is 1, 2, 3, all the way up to 0s to 255. It could be any one of those things. So this is a 10.0.0/24 network, which means the first 24 bits or the first three octets are fixed as 10.0.0, and the last octet can vary from 0 to 255. Okay, so we are showing some examples here: 10.0.0.1, 10.0.0.2, and 10.0.0.3, and host 3 and devices here. And there is an IP address which is also allocated to this router-looking device, which we will soon tell you that this is a NAT device. An IP address is also allocated to this device, which also resides on the same network. There is a physical interface here which is connecting this router-looking device, the NAT device, to the internal network. Okay. Now, all the IP datagrams or packets with source or destination in this network will have 10.0.0.0/24. One of the IP addresses here for source or destination, as usual. Okay. But when any packet from this network goes on the outside network for the rest of the internet, none of these IP addresses 10.0.0.1, these are designated as local IP addresses or internal IP addresses. These IP addresses are not globally routable. They must be translated into something which is globally routable. And all datagrams or IP packets leaving the campus network must have some IP address, must get translated to an IP address which is globally routable. In this case, this is a 138.76.29.27.7 IP address, which is the outgoing interface IP address of this network address translation device. Okay. While all these IP addresses, all these packets which are coming from different internal devices, they get translated to the same IP address, the port number is going to be different. That is how you will distinguish who is sending the packet, from the internal network. Okay. So as far as the outside world is concerned, all the devices in the internal network, they are represented by just one single IP address, which is 138.76.29.7. And as I said, the packets coming from different internal devices, they will be translated to the same IP address, but carrying different port numbers. Okay, let's take a look at that, how the NAT is implemented. Okay. So this NAT device here is translating all the IP addresses into a single 138.76.29.7 kind of IP address. So initially, let's consider the case when a packet is sent by one of the internal devices to somewhere outside in the world. Okay, so host 10.0.0.1, this guy here, 10.0.0.1, sends a packet, and in this packet, the sending IP address or the source IP address is 10.0.0.1, and the source port is 3345, which is picked by the operating system. The destination IP address, which is somewhere outside in the outside world, is 128.119.40.186. We don't know where that is, but this is definitely somewhere outside beyond this network address translation device. And I'm trying to access port 80 of that device. Maybe if an HTTP server is running on that device, and then I'm trying to access the web page on that particular IP address, hosted on that particular IP address. Okay. Now, when this packet goes to the outside network, this packet gets translated. And if you look at this packet which is going out, this number 2, the source has been replaced from 10.0.0.1 to 138.76.29.7. The port number has also been updated to 5001, which is again a port which is picked by the operating system of this network address translation device. At the same time, the NAT router or NAT device, while it changes the IP source address from 10.0.0.1 to 138.76.29.7 and the port number from 3345 to 5001, it must make a note in its network translation table. So network translation table will be populated. So WAN side, wide area network side address is 138.76.29.7, port 5001. And the local or internal side, local area network side address is 10.0.0.1 at port 3345. Okay. Now, when this packet goes to the destination, which is somewhere at the other corner of the world, the response might come back. And the response will come back not for this 10.0.0.1 guy, because there is nowhere in the packet 10.0.0.1 has been replaced by 138.76.29.7. So when the response comes back, the response will be destined for 138.76.29.7 at port 5001. When the reply arrives, this network address translation device, NAT device, will receive this packet where the destination address is 138.76.29.7, port 5001. It will immediately look this up into this NAT translation table and figure out, this is corresponding to a LAN side address of 10.0.0.1 at port 3345. So the packet will get retranslated. The destination address on this packet, number 3, will get retranslated into destination 10001 at port 3345. So this guy 10001 would not even notice that its data IP datagram, the source address was translated by the NAT device. The NAT device received the response and retranslated the IP address and rewritten the IP address as 10001. Okay, so this will be transparent to 10001 that it is running behind a NAT device. It would be working as if it has reached the destination at port 80 and has received a response from that. Okay. So network address translation, all devices in the internal network, they use private IP address space. Those 10.0.0 kind of IP addresses are private IP addresses. They are designated private IP addresses. There are ranges of IP addresses which are designated as private, and these private ranges are 10.0.0/8, which means the first octet as 10 and the last 3 octet could be anything. In the previous example that we considered, we fixed the first octet as 10 and the next 2 octet we also fixed those, and that we only varied the third octet. We could have left fixed the first 2 octets or only the first octet. Only the first octet is fixed in the private IP address space. Similarly, 172.16/12 is another IP address space. 192.168.00/16, which means the first two octets are fixed as 192.168 and the last 2 could be anything. I can use this 192.168 and I can also fix the third octet for this IP address range as well and use those as internal or private IP addresses, which will eventually get translated by a NAT device. So what are some of the advantages of the network address translation? There is just one IP address is needed from the service provider for all the devices. I don't need a bunch of IP addresses, which could be costly. I only need to purchase one IP address. And then I also save on the wastage of the global IP address space. Okay. Another advantage is that I can change the addresses of the host in my internal network without actually notifying the outside world. It would not matter to the outside world if an IP address of an internal device is changed. I have introduced 17 new devices with 17 new IP addresses, or I have turned off some of the internal devices. Okay, so it would not make any difference to the rest of the world. Similarly, if I change something on the outside world, if I change my internet service provider, I don't need to change the addresses of the devices in my internal network. Okay, so these two things work independently as long as you have this NAT device sticking in between. And finally, there is some security provisioning as well, because the devices on the internal network, they are not directly accessible. They can only be accessed. When they send something through the NAT will make a note in their NAT translation table, and when the response comes back, it will be sent to the internal device. Okay, nobody sitting outside can launch a connection to an internal device because they would not have an entry into the NAT translation table. But imagine you might have a Skype client running inside your internal network. How would somebody access you from sitting from outside? Maybe in that case, you will have to use some external assistance. Somebody else will be representing you in the outside world. Okay, we will not go into the details of that, but it is possible. There are multiple ways you can try to access the device internally, but by default, you will not be able to access the devices. Somebody sitting outside your network will not be able to access a device internally. So if I am on the university network, I have an IP address which starts with 10.0.0. something. Then somebody who is outside my university network will not be able to access a web server that I might be hosting on my machine. Okay. So the recap of implementation of the NAT device, a NAT router must be transparent in that for the outgoing datagram, outgoing IP packets, it should replace the source IP address and port number of every outgoing IP packet with the NAT and IP address of the new port number and the new port number. Okay. And the remote clients will respond to by using that NAT IP address and the new port number as the destination address in their packets that they would send back to the NAT. So the internal packet which is passed through the NAT will rewrite the source IP addresses, and the remote guy, which is beyond the NAT, will respond back to the NAT address. And also the NAT device should remember in their translation table whatever translation that they have done, whatever internal IP address and port has been translated to an outgoing IP address and the port number. Okay. And for an incoming datagram which a remote guy has sent, it should replace, by using the NAT translation table, it should replace the NAT IP address and the new port number by looking into the NAT translation table to the source IP address and the port number stored in the NAT table. So network address translation has been controversial for various reasons. First, people argue that routers should only process up to layer 3. Why you are playing with layer 4? So NAT is sort of a router. Why is it playing with port numbers which are layer 4 addresses? Why is it playing with layer 4? Similarly, address shortage should be resolved by IPv6, not by using these NAT devices which are breaking the router functionality by looking above layer 3. They are also trying to process layer 4 and violating the end-to-end argument as well. So NAT devices have been controversial because the end-to-end argument is violated. The port numbers are manipulated by the network layer devices. The network just does not remain a simple IP delivery platform. So NAT traversal, what if a client wants to connect to the server behind the NAT? This is the same question that if I am on university campus, I have a web server running on my machine, I have an internal IP address, how would somebody sitting outside access me? We said that for security purposes, they should not be able to access me. But what if I am running a web server that I want to be visible outside campus? How would somebody be able to access that web server? And we said that there are solutions existing for this. But besides these controversies, besides these arguments against the NAT is here to stay. It is very, very widely used, extensively used in homes and institutions and 4G, 5G cellular networks. So NAT is one kind of a middle box. There is a lot more kind of middle boxes. For example, intrusion detection is done through middle boxes. WAN optimization, wide area network traffic optimization is done through middle boxes. Protocol acceleration is done through middle boxes. IPv4 to IPv6 translation also through middle boxes. Transcoding, where a large web page is transcoded into a smaller web page, images sizes are reduced, is also done through middle boxes. And similarly, in your cellular network, modern cellular network, there is a backend evolved packet core, which are also implemented as middle boxes. Okay, the RFC definition. RFC stands for request for comments. These are the standard documents which list all the protocols and interfaces that should be used over the internet. So RFC definition of the middle boxes is that middle box is any intermediary box performing functions apart from normal standard functions of an IP router on the data path between a source host and destination host. So far, we had learned that between a source and a destination, there are only routers in between. But middle boxes are devices which do something more than the routers do. Routers are dumb devices in the sense that they only forward the packet from an incoming interface to an outgoing interface. Middle boxes are more intelligent. They might block some of the unwanted traffic. They might do something else with the traffic, rewrite some of the traffic, maybe do some counting of the traffic. Middle boxes are very, very widely deployed. 1 in 3 network devices on average is a middle box across the internet. Okay, so middle boxes are everywhere. You will see the middle boxes as network address translation devices in home, in cellular network, in enterprise and institutions, campus networks. You will see firewalls and intrusion detection systems in institutions, service providers, corporate networks, and ISP networks. You will see middle boxes as load balancers in corporate service provider, data center, and mobile networks, and also application-specific middle boxes in service provider networks, institutional or enterprise networks, and also on content distribution networks, on CDNs. You will be able to see these middle boxes. Okay. Similarly, you will be able to see middle boxes as caches for acceleration of the web content, quickly getting the web content, getting the responses. In service provider networks, they often install caches. Mobile networks and CDNs, they install caches as well. So we saw that network address translations boxes, NAT boxes, were controversial. It's not just the NAT boxes, which is one type of the middle boxes which are controversial. Middle boxes in general are controversial. They make the network extremely complex, and we wanted to keep the network very simple. And that is why we had this end-to-end argument that the complexity or intelligence should lie on the end devices, not on the middle in network infrastructure. But middle boxes make the network intelligent. At the same time, they introduce complexity, and hence they are controversial. So recall the end-to-end principle, which wanted to keep the network simple. Some of the features can be implemented at the end host, but network operators cannot force what happens at the end host. So these are needed. So middle boxes are needed by the network operators, because if we only keep the intelligence at the end devices, network operators will not have any control on those end devices. And the network operators do need control for various reasons. For example, for making their network safe, they want to install firewalls to increase the performance of their networks, WAN optimizers, load balancers. They also want to reduce the cost of their networks by using caches, by using load balancers, and many other middle boxes. Okay. So this finishes the discussion on middle boxes. There is a lot more on middle boxes which is available out there. There is a discussion of middle boxes in the book as well. So please feel free to read the book. We will have a couple of more presentations. One would be on link layer, and one may be on SDN, or at least one of those two. I will finish the discussion on middle boxes here, and we'll move on to the next presentation.